All right. Well, first of all, it's super awesome to see all of you guys and all the people online. It's great to see so many different areas, countries, applications. That's why we do this. We try to build MFEM so it's useful, and it's very rewarding. And we'll see that it is useful. If we can help you in any way, please reach out. That's why we're organizing this workshop, to learn from you. This is called the state of MFEM. So this is not about technical developments. That's what Veselin is going to talk after me. This is about the project as a whole. And Aaron did mention that some of you are new. So here's MFEM in one slide. After this, you're supposed to know everything about it. It's a finite element library. There are other finite element libraries, but this is the one we developed because it has unique combination of features that are important for us and for the application that we do. Some of the main things are that it can discretize pretty much anything, any PD that you can think of on different grids, not just quads and hexes, but also triangles, mixed meshes. Adaptive mesh refinement, both conforming AMR on simplices and non-conforming AMR on quads and hexes is very important, enabling technology for us. You have bilinear and linear form for many kinds of PDEs, which makes it very easy to build a multiphysics application, a high-performant multiphysics application with MFEM. That's one of our strengths because we are targeting high-performance multiphysics applications across, the other side of that fence at Livermore. However, the methods and scalability are very big focus for our team. Arbitrary order spaces on arbitrary order meshes. MPI scalability and GPU acceleration. We have big supercomputers here, as you probably know. The next one, El Capitan, is coming very soon. It's probably going to be the biggest supercomputer in the world. We have to run on these machines, and we have to run on those machines efficiently. And that's important for us. But we also want to do research. And so in MFEM, you can start development on your laptop, do some research, and then scale this up to the big supercomputers. In addition to discretizations and kind of plain finite elements, we also do a lot of work in meshing, in solvers. And so we're integrated with a lot of packages like Hyper, Sundials, pretty much any numerical method package that you can think of. We probably have an integration that is very easy to use and can pass discretization information back and forth, including, for example, AMG preconditioners, all the spaces, all physics, if you wanted a multi-physics application. And that is including GPU solvers like NGX, for example. And then we have the visualization. We have our own GLVis. I see the GLV stickers went away, so that is popular, I guess. But we also support, of course, more heavy-duty tools like Visit and Paravia. It's all free, and it's been part of all the major efforts in the Department of Energy, I would say, over the last decade. And these are just some examples of our applications and the kind of two canonical papers, one from 2020 and one that we just published in 2024. All right. There are a lot of developments over the last year in quite a few of these areas. I'll tell you a little bit about what's happening with AMR. HDG, I didn't find it, but it's one of the new improvements that Jan has been working on. And what's the connection? Jan has been working on. He's going to tell you about it. He has been working on GPU acceleration, improved GPU acceleration, and also a new release of GLVis after 2 years of a break. And that's just covering just to the surface. You're going to hear much more in the talks that are coming up. All right, I want to tell you briefly how we got here. We've been really doing this for a long time. This project started in 2000, Texas A&M University. We had a class, and we started writing a research code called AGIFEM. A&M is also the Aggies, like UC Davis. And the original contributors were a lot, but the main ones that are still with us, Veselin, me, and Stan Tomov. You might have heard that Stan passed away unexpectedly a couple of weeks ago. He was really great guy, very fine person, and amazing scientist that did a lot of things in high performance computing of great consequence, but in particular, he was there from the very beginning of MFEM. And we did that mostly because we needed it for our internships here at Livermore, and then we wrote citations with that code. This was still kind of not a professional code. The real professional MFEM started around 2010 when we got the BLAST project, which was an LDRD here at Livermore that motivated how the methods, non-conforming MR, parallel scalability. These were the main developments then. And we created the repository in May 2010. So it's, 14 and a half years at this point. Veselin, me, Rob Ribbon, and Truman were some of the first people that committed to this repository. And then the website went live in 2015. Things in the lab were not as open back then. You can see the history of Livermore open source software here. 2017, we were allowed to actually move our development to GitHub. That was a very, very big step. Before that, we just pushed releases. And from that point on, the project has been fully open. Almost everything we do in MFEM is fully in the open on GitHub. Maybe that's why we have 500 branches. I don't know if that's a positive or negative, to be honest. But after 2017, the team really expanded and includes a lot of external people. 2017 was an important year for us when the Exascale computing project started and the seed co-design center that we led here from Livermore began. MFEM played an important role there. That's how we had a lot of focus on GPU development, partial assembly, matrix-free methods. You will hear about those things later. The ECP is done now. The ECP officially ended at the end of 2024, or kind of mid-2024. And so this year, the focus for us are El Capitan, the new machine that is coming up, Mari differentiation, and then applications, taking all these developments funded by ECP and by our internal applications and making them available to more and more applications. Okay. Any questions? You can interrupt me anytime, by the way. I think for a lot of you, this is maybe known, but for everyone. Okay, so depending on how we count it, MFEM is either 24 and a half years old or 14 and a half years old. We celebrate both. Okay, this is the history in terms of the code. So this is from the first official release, 1.0, where MFEM was 22 lines of code. The latest release, 4.7, which was in May this year, where we have somehow ballooned to 420,000 lines of code. That's not the intention. We always try to keep MFEM small. It's a testament of the fact that we have more and more applications that need more and more capabilities. We only put things that we think are critical. A little bit of a hiccup here. I'm not exactly sure what's going on. But other than that, I think the curve is pretty clear and consistent. So I guess this is the point where I say that the state of MFEM continues to be strong and we're going forward and upward as in the past. These are the main releases here. As you can see, 1.0, 3.0, 4.0. We are due for another major release and we want to have another major release and we heard about it. But we want it to be a breaking release, so we need more time to focus on it, and it's been difficult to find the time for that. These are the actual sizes. It's almost 4 megabytes at this point. Luckily, network bandwidth and storage has caught up with us, so 4 megabytes in 2024 maybe is comparable to 20K, but I don't know. So the source has been growing, as you can see, quite significantly. The community also has been growing quite significantly. That's another sign of things going well. We are at about 150 contributors to the master branch, to the main branch. There are way more people than just the Livermore team. We have this organization, the MFEM organization on GitHub. You kind of need to join that if you want to contribute. We also periodically send announcements there. Almost 700 people there. That's the GitHub community. And then we're almost at about 1,700 stars, which, for a relatively niche mathematical project is actually quite successful. So we're happy with that. Some of the managers look at the stars, so it does make a difference.
That's a magic.
That's maybe. Okay, so these are the main contributors overall in the repository, and the top really here should really be John. He kind of there was some issue here, but imagine that John sits here, then me, Mark, Will, Veselin, Johan, Keaton, Jakob, and Werner. A lot of them actually in the room here. And you can kind of see how active what happened after we actually were able to work directly on GitHub in 2015 here. In terms of how wide this has spread, we have a lot of interest, having 50 visitors, unique visitors per day, maybe 200 downloads and clones per day, around 100 per thousand per year. 120,000 countries overall. This is the map. I don't know if you can see well, but we're missing a little bit of Iceland and Greenland. Again, I don't quite understand how we can get there. And also a little bit of Africa and South America. So if you know somebody, please let us know. Yeah, it covers all the continents. Let's put it this way. And then we organize these workshops. And we have the tutorial, we have an AWS tutorial that's hosted by AWS every year for free. These events usually gather around 200 people and at least 200 registered people. So there's a lot of interest, and the interest continues to be strong. And we're happy to help as much as we can. Of course, it's also great if the community steps in and starts helping itself. And that's one of the things we want to see with the community going about. This year, I already mentioned 200 plus registrations from 100 plus organizations and 25 plus. Okay, what happened last year? We had one release, 4.7 in May. That took about 7 months to develop, 42 different contributors. This is the course visualization of people working on different files. And I think it's 1 day per second or something like that. So you can see the activity and the spread. 166 pull requests, and 50 issues, 25,000 lines new code. This is code that needs to be reviewed. So maybe we don't actively are looking for reviewers, but if you want to be a reviewer, please let us know. We could use help with reviewing all these contributions. And there's a lot of new features there, like improvements in meshing and NURBS functionalities, CAD/FEM integration rules, new framework for hyperbolic conservation load, precision, low precision, single precision support, GPU accelerated digit diffusion, the ability to runtime select on GPU device with Hyper. Veselin will tell you more. These are the top 10. Yeah, the top 10 contributors. And you can see, for example, folks like Sebastian here, was at AWS and Palace Code at that point, Ego, who is in Delft, that are not, and Will at this, Will now is at Portland State, that are not here at Livermore, but they're certainly main MFEM developers. This is MFEM 4.7. We also released a new version of GLVis, and we have not released a new version in GLVis for more than 2 years. So this has been a while. We actually released 2, but the second one is kind of bug fixed, so let's just call it 1. GLVis 4.3 in August. This had a lot of cool things, updates, but also new features like being able to visualize quadrature point data that I think a lot of you may find useful if you have data at points at the quadrature points and you want to look at it. We have several options for that. I will show in a second. Support integral elements, 1D stuff, improved auto refinement, and being able to format the different numbers we display, but also a lot of bug fixes, new improvements. And after we released GLVs, we also updated the PyGLVs repository and the GLVs.js, the JavaScript version, as well as the GLVs website, a live version that we have here. And I just want to show you here the quadrature point visualization. Here, this is one way in which you can visualize, which is lower the required piecewise constant data of the quadrature points. And then with the capital Q key, you can switch between projection, interpolation, and this other view. This has all been updated. The main contributors for this are Jan and Justin, and me a little bit. Is you start seeing some names repeating here, like Jan, one of our new young developers and stars on the team. And then we also released, not we, actually, Sunichi released a new version of PyMFEM if you use the Python wrapper. That code up to version 4.7. It was also released 4.6. Sunichi Raiwa from Princeton Plasma Physics Lab has been leading this effort and pushing on this. But this year, Justin also helped quite a bit, and Justin also is present in appears twice in this list of top contributors. Thank you all for your hard work on this. I know this is not everyone, there's a lot more, but we've been pushing strong and having major advancements this year as in the past. All right. So I have in the following slides, I wanted to kind of give a very brief introduction to where you can start. Aaron already mentioned some of this, and I also want to introduce some notation or mention some things that will probably show up in the following talks, at least so you guys once, if you're not familiar with it. If you're interested in MFEM, really the first place to go is the examples. Examples are the building blocks for different small PDEs that you can take, build on, combine, and we have quite a bit of them. They also can be seen as tutorials for the MFEM features, but from the examples, then you can build bigger mini apps that go into full applications. You can just click the examples tab here or go to mfm.org/examples. And then you can filter on the examples page. You can filter by type of PD, discretization, and so on. One step further are the mini apps. The mini apps have some physics. They're not intended to be educational. They're intended to drive toward the full application, but they're not a full application. They're the framework for it. We have quite a few in the mini apps subdirectory, but I want to point out two that I feel have been the most impactful, successful. The electromagnetics mini apps. This is if you're interested in solving electromagnetic problems, and we have electrostatic, magnetostatic, transient Maxwell. The Joule mini app is also very popular with transient Joule heating. Mark is the expert on this, if you as well as others, but Mark has written a lot of those and has worked with electromagnetics for many years. If you have any questions, please let us know. These are mini apps on which people have built full applications. The other mini app is the MFEM mini app, and that was already mentioned. That's for incompressible flow. Julian is the author of the MFEM mini app that has also been used and continues to be actively developed for a variety of applications. If you're interested in compressible flow, please reach out to us. There are many others, but these are the two that I would say are probably of interest to most of you. Now, these mini apps, there are many applications, large-scale, high-performance computing applications that have been built on top of MFEM. Some of them are open source, some of them are not. One of our internal applications is the BLAST code, and this is an example of a simulation of IC, inertial confinement fusion. The National Ignition Facility is somewhere there, as you probably know, one of the biggest laser in the world, 192 lasers, recently achieved ignition. Topology optimization, this is the little code here. Additive manufacturing and shape optimization also. We work with industry, both kind of big industry, as well as small companies like Forum. Tokamak fusion, we're very interested in fusion, both ICF and magnetic fusion. So this is tokamak simulation. This is another simulation from tokamak, actually Chi did that, we see in the audience. There's also some kind of help, I would say, application like MRI modeling, art modeling. It's kind of very interesting, and things that like just interesting things like electric aircraft that people do. This is just a sampling. Of course, people do many more things, but it's an example of what you can do with MFEM if you choose it as the foundation of your application. Okay, I do want to tell you a bit more about the BLAST code because it will be mentioned through the talks today and tomorrow. This is a multi-physics code that combines compressible hydrodynamics with radiation diffusion and electromagnetic diffusion. It actually uses all the spaces in the Durand complex here. We use H1, denoted as H grad, where the degrees of freedom are generally nodes of the mesh for the velocity position. We use H curl for the electric fields, H diff for magnetic fields and for fluxes, and L2 for things like density and energy. Together with all the differential operators between them, solvers for all of this diffusion points of this physics. So all of this is motivated by this application. All developments in MFEM are motivated by this application, and this is at high order. LLNL code, which means that you have a Lagrange phase where the mesh moves following the flow, the physical velocity. You solve a system of conservation laws. So all elements become current right away in the first step. And so that's why we support arbitrary order elements efficiently. Then you have a Eulerian phase where you optimize the mesh. And you do that by solving DG advection in pseudo time. That's why we have high performance DG. That's why we have very advanced methods for mesh optimization. And there's a lot of research in not just the kind of fundamental mathematical methods, but also physics-specific things like artificial viscosity, closure methods, monotonicity, and quite a few papers that we've written in this area, some of which are listed here. So you will hear BLAST. BLAST is part of a bigger code called Marble. If we say Marble, this is the Marble logo here. We really mean BLAST in the context of this meeting. And there's also a Miniapp for just the Lagrange phase of BLAST that's called Lagos, and another Miniapp for the remap phase that's called Ramos that may come up. Okay, I also mentioned SEED. SEED was the Center for Efficient Exascale discretizations in the Exascale Computing Project. This is one of our first meetings here. Yeah, you can see Vladimir here, and that's that I don't see you from this angle. Are you there? Oh, here next slide. Sorry. This was a really great project, maybe one of the best projects I've been part of, where we focused on porting codes. MFEM was one of the main codes to GPUs and enabling our large-scale applications to work well with high-order methods on GPUs. So this, few application targets in addition to BLAST there. And I just want to share this slide. As I mentioned, the ECP wrapped up. It's kind of the final results. This is a slide from the director of the ECP, Lori Daishin, who is in this lab. The relative improvement in different applications, including the work contributed by us on the SEED, before and after the ECP. The goal for the ECP was 50 times improvement, and that's kind of what we got in hardware. But as you can see, some applications got 500 times, so a factor of 10. And this is because they didn't just move to the new machine, they changed the algorithms. And that's one of the things we did too. We changed the algorithms. And that's one of the hard things when coding to GPUs and when doing how the methods really well. You need to look at different algorithms. The way we kind of approach this is by this finite element decomposition. Again, something that should be familiar to some of you, but maybe not to everyone. It's how you decompose a finite element operator into a product of matrices, each of which enables or exposes another level of parallelism. This P operator goes from global true degrees of freedom in parallel to local degrees of freedom on each processor or each MPI rank. The G operator goes from the local mesh to values at each element decoupled from each other. And B goes from degrees of freedom on each element to quadrature points. D is the local operation on quadrature points, and then the transpose assemble from quadrature points to element degrees of freedom to local degrees of freedom. Please do not join Zoom. That's one of the reasons not to join Zoom. And if you think of the operator this way, in this decomposed form, it allows you to peer in. It splits the different components that are responsible for different things. And in particular, for us, it was very important what we compute and store, because performance really is governed by memory transfers these days, not by the flops. And so we just kept this thing called partial assembly, no assembly required, where you just compute and store the data at the quadrature point, and everything else you compute on the fly. That was an important advancement that really enabled the seamless integration of adaptive mesh refinement, high performance higher methods, GPUs, and it's also AV friendly. So you will see this finite element decomposition referenced multiple times. Based on the finite element decompositions, we were able to restructure the code using C++ lambda. That's why we moved to C++ 11. Exposing the arguments of each kernel, and the kernel is a simple loop target a variety of backends, including Oka, JIT compiled libseed, one of the another main product that we developed in C that provides high performance kernels, these finite element operator evaluations. And with that, we can now have code that's runtime selectable backend. You can executable, runs on CPU and GPU, highly performant on the GPU. And for us, this is in some sense an old thing. We get GPU support in MFEM in a main release for more than 5 years since MFEM 4.0. These are just some examples of the performance, and I've shown this before, so I'm going to go very quickly. Some generations of GPUs from P100 to H100. In this type of plots, we have problem size versus throughput. For a test problem, this is the so-called seed bake-off problem. This is BP1. Different curves of different orders, and it shows you that for the same number of degrees of freedom, higher order gives you better performance. This throughput is inversely proportional to time, so high is better. And one thing you can see here is performance portability between NVIDIA and AMD. The use of tensor cores, we experimented with this. And then, I don't know, 3 times improvement in the total performance just by moving to 8100 GPUs. And I have some papers here if you're interested to learn more about this work. Okay, this was a test problem. This was a benchmark. Here's how this impacts our C codes. Is the blast code. And some test problems from the blast code. And these curves are on different architectures. These flat curves here, CTS, this is a CPU system. ATS and EES are GPU systems, and ATS2 is our current system, Sierra. EES3 is an early access system to El Capitan using the AMD MI250X GPUs, and you can see it gets much bigger performance, kind of similar plot. And that's in all of the phases, in the overall time loop, in the Lagrange phase, in the remesh phase, and the remap phase, these phases that I mentioned. the improvements are, an order of magnitude moving to GPUs. It is a very different way of working. Once you switch to GPUs, it's more coming back after that. So, but it is not an easy thing, and it's one of the motivations to build on top of MFEM, where we have done the work for you, and we will continue to work. All right. Let me go very quickly over a few of the main features in addition to GPUs that folks find interesting, and I'll kind of illustrate them in the setting of the decomposition. Adaptive mesh refinement, as I mentioned, we have it in the very general settings. In the decomposition, this really gets encoded in the G and the P operators. It is very general. It's at the kind of library level, very high performance. This is scaling to 400 times 400,000 MPI rand. It works in applications. And it's something that a lot of our users use. I wanted to point out that we have recently revitalized our efforts in MR this year. Dylan at Livermore and Hugh at AWS really pushing on this. And some things that are coming up that might be of interest to you. Full HP FEM. So far we mostly had H refinement with a fixed P, but now we can vary both H and P. The support for general anisotropic refinement, where when you refine anisotropically, it doesn't have to be in the middle. You can have graded refinement or one refinement. And then also the ability to use submesh with adaptive mesh refinement. Submesh is one of our capabilities where you could do multiphysics by extracting portion of the domain. In the past, this only worked for compounding meshes. There's work now to work with adaptive mesh refinement. You can imagine that with AMR meshes, that is not trivial. But that's both of these three have a PR associated with them, and they're coming up next year. Another important piece of work that's very beneficial to users that we've worked on is lower the refined, and we use this both for transfer and for solvers. It is very important when you don't have a full matrix. How do you precondition a matrix like that? And it turns out you can essentially sparsify this B operator, taking a higher grid with a higher data and connecting it with lower the data on the refined grid, where the degrees of freedom, you can basically move the degrees of freedom with identity. Turns out that if you have the right higher the basis here, you can get spectrally equivalent mass and stiffness matrices for all the spaces in the Durand complex. And so you can still be matrix free here when you evaluate the operator, but here you can assemble because now you're sparse and use a standard preconditioner and use it as a preconditioner for this matrix free evaluation. And that works really well. It's known that this worked for H1, but we've shown that it also works for HCRO and HD for the magnetic diffusion and part-based out. Yeah. And in MFEM, using this MOR solvers is a one-liner. It works on the GPU, and we have a really detailed paper where we compare all the stages of the AMG setup, the LR assembly, the hardware setup, kind of the setup phases, the application of the operator, and the application of the preconditioner, and how things compare with CPU versus GPU. So solvers are another main research area for us, and another areas where MFEM really delivers state-of-the-art cutting-edge algorithms to the users. And this is just one of the problems we solved, where we're getting 10 plus gigadose performance per second out the code. Okay, the last thing I wanted to highlight is DFEM. You will also hear DFEM and automatic differentiation. That is another main area of development for us. This is really focusing on the D operator here. If you imagine design optimization workflow where you have parameters, you mesh, you perform simulation, you solve, you discretize, you solve, and then you evaluate functional and just parameters. You want to be able to compute the derivatives of this functional with respect to the parameters. So you need to differentiate, in particular, your operator. As a first step, at least the Jacobian. You can do that in the finite element decomposition. Actually, it turns out in a very straightforward way. this is the linear case. In the nonlinear case, you have a solution and parameters coming in at quadrature points in certain ways. The parameters may come as a grid function. They can come in ways. And then if you want to compute the Jacobian, it turns out you just differentiate. You compute the local Jacobian at quadrature point by quadrature point independently. And you get a partially assembled operator, Jacobian, just in the same form as any other partially assembled operator. So the upshot is, if you have a partially assembled version of a nonlinear form, you get the derivative, the Jacobian, kind of essentially for free. Again, in matrix free form, you still need to precondition that, of course, and that's where the solvers come in. And we do this in collaboration with Enzyme to perform this local differentiation. Julian will tell you more about this in his talk. Okay, so I want to spend a few minutes on talking about next year. So for us, El Capitan is going to be at Livermore a main focus. The machine is going to become available, and we're gonna run at scale there on the MI300 GPUs. There will be additional porting, optimizations for it. I would say the second main thing for us is differentiable simulations and pushing on the work in DFM. We want this to be part of the next release. We want it, of course, to work well on GPUs, to continue to collaborate with Enzyme, and to apply to problems like design optimization and some of our big codes, the multiphysics codes, which is quite challenging. Of course, we're going to do much more, continue to do research and development in many different areas. Compressible and incompressible flow, fusion, magnetic fusion, and ICF. These are important application areas for us that we continue to be interested in. Of course, structural mechanics too, usually more interesting, usually with contact and other incompressible regime. On the fundamental finite element things, I mentioned several AMR improvements. Pyramids are coming, support for pyramids and mixed meshes. We want to look at how the simplexes and being able to be more efficient on how the simplex meshes, because they're easier to mesh. Additional improvements in matrix-free solvers. These are all areas in which we want to continue to work. And then in general, more robust methods for meshing discretization solvers that are automatic, that could be used in this optimization workflow, for example, meshing, automatic mesh, without need for intervention. Okay, the next release, MFEM 4.8 is planned for March. Alan said we're going to think about it. I think it's kind of pretty clear we're going in the direction of switching to C++ 17 in the next release. And this is just kind of, this is a short summary. We have a much bigger planning document internally. Some of you have seen it. If you have other suggestions, if you think we're missing something major, please let us know. These are some of the ways in which you can contact us. Okay. The resources were already pointed out, the website, the GitHub repo. There's a lot of publications if you want to kind of be on the theoretical side. And everybody is welcome to come and contribute to a very welcoming team. And these are some of the folks here at Livermore that are behind MFEM, together with their GitHub handles, so you can get a hold of them. Thank you from all of us.